Okay. Uh, yeah, we are live. I hope you guys can hear me what I'm saying and you guys can see the presentation as well. So we will wait for a couple of minutes before we start. Um, okay. So yeah, so we can start now. It's almost time. So welcome everyone. Uh, Welcome to this tutorial session by me. So in this today's session, I will be discussing questions on maxima minima. I will be discussing questions on uh, Lagrange multiplier principle. Okay, uh, we will solve a few exercises, and if you find any difficulty understanding any argument given by me, you can raise your hand. You can ask question. You can write on the chat, uh, so we can have a discussion the way you like. Okay. So in order to minimize the use of bandwidth, I will switch off my video and then we will start the presentation. Okay, looks good. Um, so let me introduce myself with a formal introductions. I'm Prerak Deep from Aizel Bhopal, and you are watching another live discussion session with me. Okay, recording of these sessions are available on my YouTube channel, named Maths with Prerak Deep. You can search this on in the YouTube search bar, and you will find my channel on the top. Uh, all the previous recordings are available on this channel. This recording will also be available by tomorrow morning. Okay, so now we can start. Let's discuss some questions. Time for discussion. Okay, so this is the very first question. It is on the Lagrange multiplier principle. So I will not go into the detail of Lagrange multiplier. Okay, but you can think of it in such a way that it is a way to find maximum value of a function or minimum value of the function. In particular, the extreme values of a function satisfying some particular constraint. Okay, so in this case, uh, you have given a function, okay, and it is satisfying this particular equality. Okay, now what is this particular constraint? This is the constant, and this constant is the equation of a plane. Okay, if you are familiar with the coordinate geometry, so you may recognize this equation as the equation of a plane. So what does it say? So this given function is defined on whole of R3. Okay, because it has three real variables, so it is defined on R3. Okay, and it is giving out a real value because x square plus y square plus z square gives you a real value. So this is giving out you a real value. It is defined on a three variable, giving out a real value. Now, what this constraint is doing is uh, is asking you to restrict your function to this plane. Okay, so let me denote the plane by p. So it is asking you to restrict your function on the plane, which is nothing but define your function on p only. Okay, basically considering your function on p only, which is a subset of. which is a subset of R3. Okay. So, and what is P? P is given by this equation x plus y plus z is equal to 12. Okay. So that's what the constraint is doing. So, okay. So this is what constraint is doing. Okay. Now further, what it is saying. So after restricting your function to P, you need to find out the maximum value. Okay. You need to find out the maximum value of f while restricting it to P. Okay. So that's what this question is uh, can be thought of as. Okay, so I hope this question is fine. So basically, what you need to do, you need to find out a maximum value of a function subject to the constraint, basically subject to this constraint, and which constraint is restricting your uh, domain, okay, to the equation of plane. Okay, so you need to say that when you take values, when you take x, y, z from the equation from a plane, what will be the maximum value of the function? That's what the question is. Okay, so once the question is clear, we can move ahead with the solution. So there is a way to characterize such kind of questions when there is a function given, okay, when there is a function given, multivariable function given, when there is a constraint given, okay, and you need to find some extreme value, which is maximum or minimum. So these questions can be categorized, these questions can be solved by Lagrange multiplier method. Okay, so what Lagrange multiplier method. Okay, so how what is this method? So we say we start with a point, let's say x naught, y naught, z naught, okay, which satisfy the constraint, satisfying the constant. Okay, we denote our constant. We think of our constant as a function on R3 because this constant is also involved three variables. So we can think of it as a function on R3, and this function can be defined as x, y, z going to x plus y plus z minus 12. Okay, so this constant is satisfied when this function is 0. Okay, so we'll call this function to be the constant function, and g being equal to 0 is the constant. Okay, so so if we say this statement that x naught, y naught, z naught satisfy the constant, in particular we mean that g on this tuple is equal to 0. Okay, which is equivalent to say that x naught plus y naught plus z naught is equal to 12. Correct? Okay, so this is uh, so this is the constant function. Now, yeah, this is the constant function. Now we have given function on R3 as as this x square plus y square plus z square. You need to find out the maximum value of f, okay, subject to constant g x y z equal to 0. Okay, so for that, the Lagrange multiplier method says that you first need to calculate the del of f, which is dou f by dou x, dou f by dou y, dou f by dou z, which is the gradient of f. Okay, so if you calculate this, you will get this is 2x, 2y, 2g. Second point is calculate the derivative, sorry, calculate the gradient of the constant function as well. So constant function was x plus, so let me write this first. Constant function was x plus y plus z minus 12. Okay, so if I differentiate this function with respect to x, I will get 1. Similarly, if I differentiate with respect to y, I will get 1 and 1 as well if I differentiate with respect to z. Now, third point is if you want to find out the maximum value of f subject to this constant, that means, so that means whatever at whatever point, so if, so basically, so whatever the maximum value will be, that will be attained by a point. Let's say it is attained at x naught, y naught, z naught. Okay, then this point needs to satisfy this constraint because it is part of the equation of the plane. So that's what is our third condition, which is equivalent to say that x naught plus y naught plus z naught is equal to 12. Okay. Fourth step is to compare the gradients. Okay. Fourth step is to compare gradient of f and gradient of g. Okay. What do we mean by compare? So del f, delta f is equal to delta g. Okay, gradient of f is equal to lambda times gradient of g. What is this lambda? For some lambda real valued. Okay, now this lambda is unknown. So the task is to find out this lambda as well. So now what do we need to find out? So what are the unknowns? Unknowns are x naught, y naught, z naught, and lambda. So we have four unknowns. So we have four unknowns. Okay, we have four unknowns. So in order to solve for these four unknowns, how many equations do we need? We need four equations. Okay, four equations are required to solve for these four unknowns. Okay, so four unknowns we need to see for Yeah, four equations are required to solve for these four unknowns. Okay. So how do we get these four equations? We will get these four equations from number point 3 and 4. Okay, so what was number 3? Number 3 was x naught plus y naught plus z naught equal to 12. So let me write these equations here as well. So x naught plus y naught equal to 12. First equation. Now remaining three equations we will get from the point 4. I'm sorry. Okay. So now what is point 4 equation? Let's solve for point 4 equation. So point 4 involves gradient of f and gradient of g. Gradient of f we have already calculated to be 2x, 2y, 2z, and gradient of g we have already calculated to be 1 comma 1 comma 1. Okay, so now we only need to compare them. So we have 2x naught comma 2y naught comma 2z naught equal to lambda times 1 comma 1 comma 1. Now why I have written x naught, y naught, z naught? Because I'm finding out the maximum value. So I'm assuming that the maximum value is attained at this point x naught, y naught, z naught. So this equality, the fourth point will hold at that point where I am having the maximum value. Okay, that's why I need to evaluate gradient of f at this point x naught, y naught, z naught. Okay, so now you can see that how do we compare two vectors? So we compare two vectors given in the coordinate form by comparing its each coordinate. Okay, if I do that, how many equations will I get from just this one vector comparison equation? I will get three equations out of it. Okay, so if I compare the first coordinate, I will get 2x naught equal to lambda. I will call it b. Similarly, 2y naught equal to lambda, I call it c, and 2z naught equal to lambda, I call it d. Okay, so I got these four equations with me. Okay, so now let's solve for these four equations. I can remove this middle one. I have these four equations now. Okay, so now if I solve for these four equations, how do I solve? I can replace value of lambda. Sorry. Hmm, yeah, so I can replace value of x naught, y naught, z naught from b, c, d in the equation A. Okay, so if I do that, what is x naught? Is it is lambda by 2. What is by y naught? It is lambda by 2. What is z naught? It is lambda by 2. Let me replace these value in the A equation. So what will I get? I will get lambda by 2 plus lambda by 2 by 2 is equal to 12, which is same as 3 lambda by 2 equal to 12, which is further same as 24 divided by 3, which is 8. So I get lambda equal to 8. Okay. So lambda is equal to 8. Now once I know the lambda, I can find out the point. So x naught is 4, y naught is 4, z naught is 4. From which equation? From this equation. Okay. I can find out the point x naught, y naught, z naught as well. And so so as a conclusion, let me write the conclusion. So the function f(x, y) equal to x naught x square y square z square attains its maximum value at 4 comma 4 comma 4, okay, subject the constant which is x plus y plus z equal to 12. Okay, now in the question it is asked to find out the maximum value. Okay, so what is the maximum value? It is the square. Okay, so maximum value is attained at 4 comma 4 comma 4. So what is this? This is 4 square plus 4 square plus 4 square, which is 16, 6 plus 16 plus 16, which is 48. So this is our answer. Okay, so let us go back to the original question. So the original question, option D is correct. Okay. Any doubt in this question? You guys can ask. If there is none, then we can move ahead discuss the next question. I will wait for a couple of minutes and then we will move ahead.
Sir, once again,
Yeah.
just quickly review the answer, please.
Uh, okay. So I'm recording these sessions. You can go to the YouTube channel, this YouTube channel, Maths with Prerak. You can find this recording by tomorrow morning. Okay. For the full description which you missed. Okay. But I will again go through this solution. So in this question, you need to find out the maximum value of this function subject to the constraint x plus y plus z equal to 12. Now this constraint is equation of plane, which is irrelevant. Uh, so the method to solve this question is to use a Lagrange multiplier method. Okay. So for that, we first identify what is the constraint. Okay. So constraint is given by x plus y plus z equal to 12. So we write it as a function. So how do we define a function? We define this as a function xyz going to x plus y plus z minus 12. Okay, so that when this function is equal to 0, it gives me the constraint. Correct? So when it is equal to 0, it gives me the constraint. Okay, now we follow these 4 steps. So first I find out the gradient of f, then I find out the gradient of g. Then third step is, so if my function attains maximum at x naught, y naught, z naught, then by the assumption that it needs to satisfy the constraint, in particular, the value of g at that point must be equal to 0. That's what my third point is. Okay. And now fourth point is that gradient of f must be equal to some lambda times gradient of g for some lambda. So in particular, I have 4 unknowns to find out: x naught, y naught, z naught, and lambda. And how many equations do we have? We have 4 equations. Okay. First equation coming from point 3, and remaining equations are coming from point 4. Okay. And I think you have seen me discussing this thing. So I will skip that. And now from these 4 equations, I just replace values of x naught, y naught in the equation A to get the values x naught, y naught, z naught. And now once I get the point where it attains the maximum, satisfying the constraint, I evaluate the value. Okay. So this is the solution. And if you want to understand it in more, if you want Okay. Uh, yeah. So now, question number two. Okay. So in this question, we have given two variables. Sorry, we have a change of variables. We have given two variables, and they have written in terms, and we have performed a change of variable over them. Uh, so now we are asked to calculate the Jacobian of this change of variable. Okay. So let us first recall what is the definition of the Jacobian. Okay. So Jacobian xy, this is the notation for the Jacobian. It is nothing but the determinant of a matrix. Uh, Now, what is this matrix? Matrix is D dx by du, dou x by dou u, dou x by dou v, dou y. Uh, yeah, there is. Yeah, dou x by dou v, dou y by dou u, dou y by dou u. So, since you can notice here that uh, when we perform change of variables, each of the coordinate x and y are is a function of two variables in itself. Okay, that's why I'm performing the partial derivative of x with respect to u, partial derivative of x with respect to v, and so on. Okay, and the Jacobian is nothing but the determinant of this matrix. So you just need to calculate the partial differentials of xy with respect to uv. So in this question, it is pretty easy because you already given the description of the function. Okay, you have already given the expression for the change of variable. So you have given x in terms of ub, you have given y in terms of ub, so you can calculate this in particular. So let me do the calculation for you. So in our case, x is given to be u square minus v square, y is given to be 2uv. Okay, so now partial differential of x with respect to u is 2u, partial differential of x with respect to v is minus 2v. Okay, partial differential of y with respect to u is uh, 2v, and partial differential of y with respect to u with respect to v is 2u. Okay, now if I plug in these value into the determinant, into the formula. Okay, let me. Okay, determinant of what? 2u minus 2v, 2v, 2u. Okay, now if I calculate this determinant, what will I get? I will get 4u square. Okay, 4u square minus of 2v times 2v. So 4u square minus will become plus 4v square. Okay, so this is what our Jacobian is going to be. So this completes the question solution. So the answer D is correct. So is this fine? This formula is fine? Is everything fine? Calculations are fine?
Yes, sir.
Okay. Okay. So now we can move on to discuss this question number 3. So in this question, you don't, yeah. So in this question, the change of variable is given by an invertible matrix. Okay. And we need to find out the Jacobian of this transformation. This question is again similar to the question we just discussed, but let me discuss, because we don't have the explicit description of xy in terms of uv, uh, but we will first find out the explicit description of xy in terms of uv, and then we will plug in, and then we will calculate the partial derivative, and then we will plug in those values in the Jacobian, uh, and we'll get the answer. Okay. So, uh, so let me just first write the formula for the Jacobian. Xy determinant of dou u, dou x, dou v, dou y, dou u. Okay, that's the formula. And now what we have given as a transformation is A is a matrix, 2 by 2 matrix, A, B, C, D. Okay, and we have given A multiplied with UB, giving me this column vector xy. So what is this? This is a matrix multiplication. And how do we perform this matrix multiplication? Is so we have 2 cross 2 matrix, we have 2 cross 1 matrix. Now the matrix multiplication is performed this way, that the first row will get multiplied to the first column of the other matrix. Okay. And how does this? This entry will multiply to this entry, and this entry will get multiplied to this entry. Okay. So, sorry, we had UV here. So we will get AUBV, correct? Now, second entry of the column vector, of the resultant column vector, will be C times U plus D times V. Okay, now we compare this with the right hand side given, which is XY. So what does this, this will give us? That this gives us the description of, okay, let me use the another page. So this gives us a description of X in terms of AB, A times U, B times V, and description of Y also in terms of UV, which is CU plus DV. Okay. So now we get the explicit description of XY in terms of UV. Okay. Um, where A, B, C, D all are real numbers. Okay. In particular, they are constant. So now uh, let's calculate the partial differentials. So partial differential of x with respect to u is a. Partial differential of x with respect to v is b. Partial differential of y with respect to u is c, is d. Okay. So in particular, the Jacobian matrix will be nothing but A, B, C, D, which is similar to finding out determinant of A. But I think in this question, they are not asking us to find out the determinant. Okay. So I think in this question, they are asking us to just find out the matrix whose determinant we need to calculate. So, so the answer is the Jacobian of the transformation is A. So the answer is A. We are getting A as a result. Okay. Because the matrix that we are getting ABCD is it is nothing but the matrix A. Okay. So is this question clear?
Sir, in this question, they mentioned A is a invertible matrix.
Yeah.
Suppose if it is not an invertible matrix, then what will happen?
If it is not invertible matrix, we don't actually need that assumption. It is we don't actually need that description because whatever the explicit description we are getting of xy in terms of uv till this point we haven't used actually in this solution we haven't used invertibility. Okay, we haven't used invertibility of a b c d, and suppose if it is invertible then the answer will be zero because the determinant of a will be zero. Sorry, if it is going to be non-invertible the answer is going to be zero. Okay, but till this point we haven't used invertibility in this question, so it is uh, I would say it is not required. This hypothesis is not required.
Sir, is it a change of variables? Is they may be considered as a linear transformations, right?
Yeah, they are defining the change of variable as this as a linear transformation in this particular case. Yes.
Okay, then change of variables may or may not be invertible, right? The transformation, right?
Yeah, it may not be invertible. It may not be uh, invertible. Yes.
Okay, okay, sir.
So, for example, in this case, this question which we have the next question in this question we have given a coordinate transformation from xy to ub such that the Jacobian is zero. Okay, then the transformation is not invertible. Okay, is it a true statement or a false statement? So it is a true statement because what is Jacobian? Jacobian is the determinant of the du sorry dx. Yeah. So what is Jacobian? So Jacobian is determinant of du dx sorry dx du dx dv dy du dy dv. Okay. Okay. So what is the transformation? Transformation is this. This is the transformation matrix, and it is given that the transformation. It is given that the Jacobian is zero. That means this determinant. Okay. This is what this is given to be zero. That means this determinant is zero. Okay. And when we have determinant of a matrix to be zero, what does that imply? That implies that A is not invertible. Okay. So hence this statement is true. Yeah. So let's wait. Um, okay, so till this point, if it is fine, we can move ahead, discuss the next question. Any other query do you have? Because now we are shifting to metric spaces. This part will be over now. Uh, we don't have any more question on this part. So before that, if you have any particular question, you may ask. I will wait for a couple of minutes.
Sir, my question is,
Yeah,
so change of variables, uh, they may be considered as a linear transformations, right?
yeah, yeah. They need not to
So
be linear transformation also. Yeah,
uh, sometimes it may not be a linear transmission, right?
correct, correct.
Okay, okay, that's my question. Okay.
Yeah, yeah. Because so we discussed one example. Yeah. So this question number two. So this change of variable is not linear. Okay, linear in terms of UV. So quadratic equations are coming in. It is quadratic change of variable. It is not linear change of variable. So,
So
but it is still a change of variable. Yeah.
can we express a change of variables into a matrix representation?
Now, if you can do that, then it is a linear change of variable. If you can, if you can represent your change of variable as a in terms of matrix, then it is a linear change of variable. For example, you cannot represent this change of variable as a matrix multiplication. You cannot find out a metric. If you multiply with uv, you get this u square minus v to uv. So there
Oh,
is no uh, such a. That's the so there are if you can write your transformation change of variable transformation as a matrix multiplication, then it is linear transformation. And any linear transformation can be written as the matrix multiplication. Those two are if and only if statement. But not every transformation change of variable is linear. That is also true.
okay, sir. Suppose um, what is the use
Yeah.
of change of variables?
What is?
Usage of.
So
Is there
it changes
to
the domain of integration. So for example, if you are integrating something, uh, or if you are, let's say you are integrating something which is a sine, if you are integrating, okay, and the limits are given in terms of xy, or maybe, so it is better to change into the polar coordinates than working with the Euclidean coordinates. Um, yeah, so it basically helps you to so one of the application is to uh, simplify the calculation. Okay.
yes?
If you change the variable,
Uh,
it will help you to simplify calculation. And
yes. Suppose,
so
uh,
I can't hear you. Your voice is breaking.
okay. Okay,
You
sir.
can repeat whatever you say. You can.
Yes, we can proceed with the next
Okay.
questions.
Okay. Okay. Yeah. So now we are going to discuss metric spaces. I assume that you all of you have seen the uh, uh, lectures on this metric space theory. Uh, uh, yeah. So I will be discussing this question. I will be discussing this question which involves Euclidean metric and supremum norm. Okay, so uh, the definitions are given in this question itself. So I will discuss these definition as well. What do we mean by that, and uh, how to understand these definition, and then we will move on to discuss this question involving the inequalities of these two norms. Okay, so this is basically defining. This is giving us a norm. It is not in particular defining a metric, but you can define a metric using a norm. So that's always you can do. Uh, I hope I am making sense to all of you. If you find anything, any argument uh, out of your scope, you can raise your hand, or you can directly unmute yourself and ask me questions. Okay, so first we have Euclidean norm. This is the usual norm which you use to calculate the distance in R2. Okay, and the supremum norm is a bit new because I because that's not very common norm we use in 12th standard. Okay, so so let me discuss the first norm that we have in our hand, which is uh, Euclidean norm. Okay, so if I assume my x sitting inside R2, that means it has two variable, two coordinate x1 and x2. Okay, so in my case, I'm taking n to be 2. So just for simplicity, just for understanding, I'm taking n to be 2. So now if I yeah, so if I uh, consider this norm 2, by definition it is given by, yeah, so by definition it is the x1 square x2 square. Okay, so now what is this? So if I try to draw this, so for example, if I calculate the length of 0 comma 1 in this norm, what will be its length? It will be 1 square plus 0 square, it will be 1. So we already know that vector, so 1 comma 0 is a vector sitting inside, 0 comma 1 is a vector in xy plane. So we already know its length is 1. Okay, so this is my vector 1 comma 0, and we already know its length is 1, and that's what we are getting out of this as well. Similarly, if you, let's say, take a different vector, which is, let's say, 2 comma 3, or let's say this is 1 comma 1 vector. Okay, so you want to find out the length of this vector, you can use this norm to find out the length of this vector as well. 1 comma 1, which is going to be 1 square plus 1 square, going to be square root of 2. Okay, so this length, so this norm you are already familiar with. Okay, you have seen this norm to find out distance between any two points as well. So in particular, you can think of this as a distance of any point in R2 from the origin. Okay, uh, or in particular the length of the vector as well. So that's what. So this is in the case of R2, which you are already familiar with. Now you can generalize this concept for higher dimensions. Okay, in particular, you can take a vector in Rn instead of just n equal to 2. You can take a vector in Rn, and you can analogously give the definition of Euclidean norm like this. So instead of just adding two vectors, just sorry, instead of adding uh, two its first two coordinates, we will add all of its coordinate. Okay, so in Rn we will have in Rn a vector will have n coordinates. In Rn, okay, so if I let me partition this. Okay, so in Rn, we have any vector x will have n coordinates, x1 x2 up to some xn. So similarly I can generalize this length or distance or this Euclidean norm in this way. Okay, so that is what given in the definition as well. So this is the first definition of Euclidean norm. Okay, now we move on to discuss the supremum norm. Okay, so supremum norm again on first let's see on R. So when we have R, so any vector in R is just a single coordinate real number. Okay, so it is just x, and if I calculate the vector norm on it, what will it be? By definition, it is the maximum of the modulus of x, which is nothing but x only, modulus of x. So in R, vector norm is sorry in R, supremum norm is nothing but the modulus of the real number. Okay. Now what happened in on R2? So if I switch for n equal to 2 case, so then if I take any two vectors, sorry, if I take a vector in R2 which is like x1, x2, then it will be the maximum of x sum, x1 and x2. Okay, so whatever will be the maximum, that will be the norm of this vector. Okay, you can always think of norm as a length of this vector, and norm can be given by, and this norm can be changed. Okay, and if you change the norm, the length of the vector will change, but it will be with respect to this norm. Okay, so yeah, so for example, if I take some example, let's say 3 comma minus 4, what will be its length? Its length will be, or what will be the norm of this vector? It will be modulus of 3 minus this. What will be this? It will be 4. What is the maximum? Maximum is 4. So its length will be 4. But if I calculate the Euclidean norm of this vector, what will it be? It will be square of 3 plus minus 4 square. Okay, that's what the definition of Euclidean norm. And it will be 9 plus 16, square root of 9 plus 16, which is square root of 25, will be 5. Okay, so you can see that same vector has different length if I change the underlying norm. Okay, if I change the underlying norm, the same vector will have different lengths. Okay, so first length is with respect to the supremum norm, then another length is with respect to the usual norm, which you are already familiar with, which is the Euclidean norm. Okay, now as I generalized uh, Euclidean norm in the case of Rn, I can similarly generalize this supremum norm in the case of Rn. Okay, so how do we do that? So if I pick a vector, yeah,
Sir, my question is,
yeah,
suppose norm 2, what will
uh-huh.
happen we are considering to norm 3 or norm 4?
If you can, so that is good question. But the point is like you need to first check that whether if you change the definition of the norm, will it first of all, if you take another norm, let's say you are saying let if I take this x1, x2, 3, okay, which how will you define that? Will you define it like x1 cube plus x2 cube, like that you are saying?
Yeah, what is the actual definition? That's my question for norm 3.
Actual definition, norm 3, it's I don't know the exact definition because I don't know whether norm 3 will make sense. But usually, how do we define norm 3? It's basically, I think we take cube root. So it's more or less like, so whatever norm you take, norm n. So it is nothing but the xi to the power n summation, okay, from 1 to 2, and then you take 1 over nth root of it. That's what the definition is. So if you take n equal to 3, so it will be cube. You are adding the cube, and then you are taking the cube root of that thing. So that's the generalization in the norm definition. But this is out of your scope, so let's not go into
Yeah,
that.
yes.
Okay.
Okay, okay, thank
Yeah.
you.
Yeah. So yeah. So now, as I generalize this norm, Euclidean norm in the case of Rn, similarly I can generalize this in similarly I will generalize this supremum norm in the case of Rn. So how do we do that? So the way to do it is again similar. So if I pick a vector in Rn, so it will have n coordinates x1, x2 up to xn. Okay, and now the norm of this vector is nothing but the maximum of all these modulus. Okay, so yeah, so that's the definition. So this is the definition. Okay, now once I assume that all of you are get familiar with the these two definitions of norm. Now the question is, uh, can we compare these two norms? Okay, can we compare these two norms? And if we can compare, then what is the relation between these two norms? Okay, what will be the inequality they will satisfy? So you have four options. First option is this, another option is this, third option is this, fourth option is this. Okay, so we will see either only one of them is true. So we'll see which one is true. Any question at this point?
No, sir.
Okay, good. So yeah, so now you need to notice a few things, that if you first let me write both of the norms. Okay, again I'm assuming that x is in Rn, and so on, and x has this representation, x is equal to x1, x2 up to xn, and it is in Rn. This is what I'm assuming at this moment. And norm of x, Euclidean norm of this is x1 square, x2 square plus xn square, and square root of this expression. The infinite norm is maximum of x1 up to xn. Okay, now you need to notice that uh, so whatever is the maximum, okay, whatever will be the maximum of these finite quantities, of these finite numbers, it will be attained by one of the number. Okay, so it will, what do I mean by that? This will be equal to some xj, where j is sitting between 1 to n. Is this fine? So for example, if I am finding out the maximum between 1, 3, 4, 5, so what is the maximum? Maximum is one of them. Maximum is coming out from one of them. Okay, that's what I meant. So it is 5. So in this case also, because I'm comparing on maximum from finite real numbers, so maximum will be an element from one of this uh, entry. Okay, so let's say xj is that entry. Yeah. Okay, so let's say xj is that entry. So in other words, because xj modulus of xj is maximum, so in other words, each of x1, so each of xi, okay, modulus will be smaller than xj for all I between 1 to n. Okay, this will hold because xj is a maximum. Okay, so this is the first thing to notice. Now, what is the second thing to notice? Second thing to notice is this, that if you square x1, if you square x1, and if you square its modulus, if you square the modulus of x1, both will be the same quantity. Okay, they will be equal. Okay, squaring a real number and squaring its modulus will be same. You can take examples, uh, which is 1 square, sorry, minus 5 square and minus 5 modulus square. So it will be 25. This will also be 25. It will always be positive, and since the and they will be equal. Okay. Okay. So these are the two things. In particular, for all I, this will true. This will be true for all I varying from 1 to. And now these are the two things. These are the two things we need to solve this question. These are the two observations we need to make to solve this question. Okay. So now, yeah. So let me write x1 square, x2 square up to xn square, and this will be equal to x1 square modulus square of modulus, correct, by 2, correct. Now I will only focus on the right hand side. So now right hand side, each of the number x1, x2, xn, each of the number is smaller than xj, correct, xj square. Each of this quantity is smaller than. So each of this number is smaller than xj, and where this I is varying from 1 to n. Okay. Oh, just a second. Okay. Uh, yes. So what I was saying is that each of xi is smaller than xj. Okay. So it is basically writing like this. So I can use this smaller than equal to sign. Correct. And now, how many times I'm adding up these numbers? I'm adding up them n times. So that's why this quantity will be equal to. So this quantity is equal to, because I'm adding this constant n times. It is equal to n times xj modulus of square. Okay, so now what relation I have gotten is x1 square, x2 square up to xn square is smaller than n times xj square, correct? Which is nothing but n times. Okay, let's keep it right there. Now you can see if I square root both side, if I square root both side, what will I get? On the left, I will get modulus Euclidean norm of x. And on the right, I will get square root of n of mod x, which is nothing but square root of n. What is mod x? Mod, sorry, mod xj. What is mod xj? Mod xj is this supremum norm of x. So what inequality I have achieved is that, which implies that Euclidean norm is smaller than n square root of the times the supremum norm. Okay, so this is our answer. So if I go back to the question, correct answer is D. Okay. Okay. So any question if you guys having, you can ask. I will wait for a couple of minutes for you to digest this whole argument. Um,
Actually, the supremum norm is always less than or equal to the Euclidean norm, right? But but in this result, it shows that the root n will makes a supremum norm will be the greater one, greater than the
Correct.
Euclidean norm. Yes.
Yes. Yes. Yeah. That is true. Okay. Anyone else? Anyone else having other questions? Okay. Um, yeah. So we can go ahead and discuss the next question, which is also on the Euclidean norm and the supremum norm. So now, by now, you are already familiar with the definition. I assume that you are already familiar with the definition. So I won't go into the explaining definition again to you. Uh, Now, in this question, we have seen one inequality between these two. Now it is uh, about the other inequality. Do we have other relation uh, which you guys just mentioned, which that the supremum norm is smaller than the Euclidean norm. Okay, so let's see how do we prove this another inequality. So we need to again keep in mind that we need to keep in mind that mind in the definition. Okay, what are the definition of Euclidean norm and the supremum norm? So again, I'm starting with x, which is sitting inside Rn. Okay, the Euclidean norm is x1 square, x2 square, up to xn square, and square root of this thing. An infinity norm or supremum norm is maximum of of these modulus. Okay, so again, uh, this maximum of these finite numbers, finite real numbers, will be attained by some xj. Okay, for some j sitting between 1 to n. Okay, one of the number will be larger than others. So we will take that particular entry and call, let's say that entry is j. Okay, so this will be xj. Now, yeah, now xj square, modulus of xj square will be equal to xj square. Okay, we have seen this last time. The square will be same. Okay, so Now if I add some positive quantity to it, it will be larger than this. It will make the uh, right hand side entity to be larger than the left hand side entity. Okay, for some positive. Okay, k. So we keep this in mind. Let's call it to be. Now we want to make on the right hand side. We want to make the Euclidean norm. So what is the quantity do we need to add? We need to add the remaining uh, squares, correct? We need to add the remaining square in order to make the right hand side the Euclidean norm. So that's what we will do. We will add the remaining quantity. So let's take this k to be summation to be x1 square, x2 square, x2 square, or better way to write it is that uh, xi square, I varying from 1 to n, and I is not equal to j. Okay, so this is a shorthand notation to write that I am excluding xj from this summation. Okay, or another way to write it like this, that I'm adding from 1 to n xi square, but I'm subtracting xj square. Okay, so I'm subtracting this thing minus the xj square, and now this summation is the summation is nothing but the norm. Okay, it is the Euclidean norm of x minus xj square. Okay, so I will, and this quantity is positive. Why it is positive? Because this, if this is positive or equal to 0, it is not necessary to be positive. It is positive or equal to 0 because the remaining xi's that I'm adding are positive quantities. Okay, so if I add positive quantities, it will remain positive. Okay, in particular, if I add non-negative quantities, it will still remain non-negative. So, so my k, which is norm Euclidean norm of x, norm of x minus xj square, it is a positive quantity. Okay, this implies this thing. So I will add this. Uh, so adding k to k in equation A. So what is equation A? Equation A is xj square is smaller than or equal to xj. Sorry, xj is. Oh, sorry. Did I? Oh, sorry. Uh, Modulus is not required. My mistake. Modulus is not required because yeah, modulus is not required. Okay, is this fine? Modulus is not required because I'm just subtracting xj square from the Euclidean norm. Okay, and the remaining will be the sum of uh, remaining will be the sum of remaining i's, which is not equal to j. Okay, so that's what I'm doing. Yeah, plus. So if I go back to this inequality or this equation, in this equation I have added k into this. I have added k such that this becomes an inequality. Okay, and now this k needs to, and what was the condition? That this k needs to be either equal to or greater than 0. So yeah, so that's what I'm adding. It is, I'm adding something which is greater than or equal to 0 to this quantity. Okay, Oh, sorry. This is not the Euclidean norm. It is still the square of Euclidean norm. Okay. This is the square of Euclidean norm. It is not the Euclidean norm exactly. It is the square of Euclidean norm. So square term will also appear here. Okay. Now, right hand side you can cancel out this thing with this. So what is remaining? It is Euclidean norm square. And what is the left hand side? Left hand side is the infinity norm square. Correct? Is the supremum norm square. And if you take the square root both sides, what will you get? You will get the supremum norm is smaller than the Euclidean norm. Okay. So this completes the proof of this question. Hence the uh, part A is correct. Okay. Now, guys, you can ask your questions if you have any. I will wait for a couple of minutes and then we will start. Okay. Let's wait for others. They might have some question. Okay. Uh, Thank you for your response. So we can now move ahead with this question. Now, uh, yeah. So this is a bit odd, but this question was remaining in my last assignment discussion. So I put it in this assignment solution. Okay. So in this question, we need to find out whether this inequality is true or false. Okay, as you can see, it is a double integral question. Okay, and the reason is the rectangle given. I need to find out the whether that is satisfy the inequality or not. So let me ask you guys, do you have any idea how to solve this question? Or first of all, is this true or false? If it is true, then how do we solve this? Do you have any idea? Because it is this is part of the previous assignment, previous to previous assignment. Okay, so do you guys have any idea how to proceed if it is true, or have you solved this question before? It is fine if you don't have. uh, I will anyway going to discuss the solution, but I just want to have some discussion among you guys so that I can see where is the difficulty understanding, so that I will more emphasis on those points rather than presenting my own proof. So I hope that all of you are comfortable with English. Uh, I know only English and Hindi, so I can't help you in there. Okay, so I think you guys have not solved this question. So let me discuss the solution with you. So this is a double integral question. Okay. So how do we deal with such questions? So first of all, you have given double integral over a region. You have given a two variable function, and there is dA. Okay. Now what is this dA? This dA is the infinitesimal area. Okay. So what do we mean by infinitesimal area? So let's recall, when you have a one variable function, you have dx there, okay, and some interval or something like that. So you have dx over there. And now what was dx? Dx was the infinitesimal, very small part of your real line. Okay, very small interval of your real line. Similarly, when you work with two dimension, so so what is the relevant small region in two dimension? It is not a segment. It is going to be a square or a rectangle. Okay, that small rectangle, small square. So in particular, this dA is dx times dy. Okay, uh, yeah, and this r is given to you is a rectangle. How do you say it is a rectangle? Because it is a multiplication of two intervals. Okay, so by convention we assume that the first interval is coming from is is from the x-axis, okay, and the second interval is from the y-axis. So it is an interval from 0 to 1 by 4 times 1 by 4 to 1 by 2. Sorry. So if I try to draw this in the on the plane, then how do I draw this? This is my x-axis, this is my y-axis, this is 0, this is, let's say, 1 over 4, this is, let's say, 1 over 2, this is 1 over 4, this is 1 over 2. Okay, now on the x-axis I have 0 comma 1, 0 comma 1 over 4 interval, which is this, and on the y-axis I have 1 comma 4 to half, which is this. And if I consider their multiplication, what will that region be? That region be this part. Okay, so in particular that region be this. So this is my r. Oh, this is my r. Okay, so all these things, okay, and now you are integrating your function, which is of two variable, over this region. Okay, like you used to do integration over of a function over a single region. Let's say this is your function and this is your domain, so you used to integrate over this region. In particular, you used to calculate in one variable case I am talking about, this area under this curve, correct? Now you will be doing a volume over under this curve, okay, lying on top of it. So it is a similar generalization of integral into variables from one. Okay, so now because now how do you write the limits in on the double integral? Okay, like in the case of one integral, I have I given to be AB, then the limits are from A to B. Similarly, you can write limits in this case as well. So the first integral sign is for x-axis. So x is varying from 0 to 1 over 4. So this is the limit. Now second integral sign is from 1 by 4 to 1 by 2. So it is 1 by 4 to 1 by 2. Okay. Yeah. So this will be the limit. So this is how you write this expression, which is not given explicitly in the explicit terms. Okay. and now you substitute your function. So I think this is fine. Now in our case, the function is given to be, so the limits are 0 to 1 by 4, 1 by 4 to 1 by 2, sine pi x times cos pi by dx dy. Okay, yeah, but we are interested in finding out the maximum of this integral and minimum value of this integral. Okay, we are not finding out calculating the exact value of this integral. So here we will use some properties of sine function and cosine function, in particular some properties of trigonometric function. Okay, so properties, in particular a property, just a simple property of sine and cos. So what is that property? That sine function is always bounded below by -1 and bounded above by 1 for all x in R. Similarly, cos function is also bounded below by -1 and bounded above by 1. Okay, so this is the property that I'm going to use. Further, you can also expect more from these bounds by considering their range. Okay, where this x is varying. So in the first case, x is varying from, okay, so in the first case, x is varying from, not in the first case, the x is varying from 0 to 1 over 4. Okay, so what happens to your function? So if you try to draw the graph of 0 to 1 by 4, okay, so let's try to draw the graph of sine function. So yeah, so this is correct. And now this is sine function graph. Okay, now what do we mean by 0 to 4? Now you see that in this function, in this expression, sine has pi times x. Okay, so whatever x value will be there, it will be multiplied by pi. So we directly multiply by pi and see the limit point. So it will indirectly be, so pi x will be varying from 0 to pi by 4, correct? If x is varying from 0 to 1 by 4, this implies that pi x is varying from 0 to 1 pi by 4. Okay, so this is 0. And what is pi by 4? Pi by 4, this is pi by 2. Pi by 2, pi by 4 will be somewhere in between this. So this is my point. So this is sine function. Okay, this in which we are interested in. So we are only interested in this part. So let me, uh, okay. Yeah, so we are only interested in, let me zoom it a bit. So we are only interested in this part, correct? So now in this part, you can see that sine, what is the maximum value of sine? Sine taking maximum value at pi by 4, which is, so maximum of sine pi x in this region is 1 over square root, which is equal to sine pi by 4, which is 1 over square root of 2, correct? And the minimum value of sine pi by x is sine 0, which is 0, correct? So what can I say? I can say that sine pi x is varying, is lower bounded by 0 and is upper bounded by square root of 2 as when x vary from 0 to 1 by 4. Okay, is this fine? Now similarly, I can work out the similar bounds for cost function as well. Okay, so let me first draw the graph of the cost function. Okay, let me first draw the graph of the cost function. So now my y is varying from 1 by 4 to my y is varying from 1 by 4 to 1 by 2. Okay, which will implies that pi y will vary from pi by 4 to pi by 2. Okay, so let me draw that first. Okay, so this is my graph of cos. Okay, I'm just drawing a arc of it, which is relevant to our understanding, our question. So this is 0. Okay, and it hits the axis at pi by 2, correct? So somewhere between it will be pi by 4, and the function is varying from pi by 4 to this region. So we are only interested in this part. We are only interested in this box part. Okay, so let me show you. So we are only interested in this box part. So in this box part, we again find out the bound. So what is the maximum of cos pi y within when y is varying from this range? It is cos pi by 4, which is square root of 1 over square root 2. And what will be the minimum? Minimum is minimum of cos pi y is cos 0, which is, cos pi by 2, which is 0. Okay, so what can you say? Again, we can say that cos pi y is varying between 0 to square root of 2, 1 over square root of 2. Okay, so cos pi y is also varying from 0 to 1 over square root of 2, and sine pi y xy is also varying from 0 to 1 over square root of 2. Okay, so these bounds we will use to apply on this integral. Before that, there is one more property. There is one more theorem that we are going to use uh, in this. So this double integral is equal to calculating these two separate integrals. Okay, so basically first calculating the integral with respect to dx, and then whatever is the remaining function you integrate with respect to y. So this is called Fournier's theorem, which we are going to apply in our case. And to apply Fournier's theorem, you only need your function f to have partial, you to have continuous partial differentiable function, partial derivatives. Now since f x y, which is sine pi x times cos pi y, is has continuous partial derivatives, we can apply Fournier's theorem. Okay, so as we apply Fournier's theorem, so we have 1 to pi by 4, 1 over 4, 1 over 4 to 1 over 2, cos pi y sin pi x dx, and then cos pi y dy. Okay. So in this case, we can further separate out these two integrals times this integral, because the limits are also independent of the uh, variable. Okay. Now sine is, we already know that sine pi x is varying between 1 over square root 2 and 0. So it is, upper bound is 1 over square root of 2, integration from 0 to pi 1 over 4 dx, times integration from 1 over 4 to 1 over 2 of 1 over square root of 2 dy. Okay. And the lower bound, we will calculate lower bound later. So if you integrate this 1 over square root with respect to dx, it is a single variable integration. You all know what does it. So it is 1 over square root will come out because it's a constant, and 1 over 4 minus 0, it's 1 over 4 times 1 over square root, again 1 over 4 will come out, and this, if you compute this calculation, so it will be 2 times 4, which is 1 over 32. So the upper bound, so upper bound of, so upper bound is 1 over 32. What the lower bound? So lower bound, so the lower bound for both of the function was 0, and integration of 0 is 0. So you will get lower bound to be 0. Okay. So this is your answer. Hence the inequality is true. Okay. So this inequality is true. Okay. Any questions? Okay, so if there is no more question, then we can. Uh, any other problem given, we have to take integration first with respect to y. You can you can apply Fumni's theorem as long as the partial differential of the function are continuous, and uh, you can take you can take the integration with respect to y first or x first. It doesn't matter. But if the limit depends on the limits of the function, okay, so limit of this integration depends on the either of the variable, then you need to be careful. Okay, so for example, if it depends on x, so you first need to integrate with respect to y, okay, so that you will get everything in terms of x, and then you integrate with respect to x. But if it is given, if the limits are given in terms of y, so you need to first integrate with respect to x, so that everything after integration, everything after the first integration, everything will come down in terms of x, and then you sorry, in terms of y, and then you can integrate with respect to y. Okay. Okay, so now we can move on to discuss this question number 8. uh, yeah, so in this question, this is a critical point question. So I will give you the how to solve this question. I won't be discussing the detail of this question. Okay, I will tell you how to solve this question. So given a function, two variable function given to you, and you need to find out the critical values of f. So what are the critical values? Critical values are those points where derivative of the function is equal to 0. So since we have two variable function, so the differential of f is this. Okay, in particular, this has to be 0. So for some xy, if it is 0, then that xy is critical point of f. Okay, so in this question also you need to solve for the partial differential of each of this function with respect to x and then with respect to y. Then you will be able to and then you will get two equations, and then you need to find out the points x y from those two equations. So partial differential of f with respect to x, it will be okay, and partial differential with respect to f of y will be, and now notice that this is always positive. So if you equate this to be 0, so you will get these two equations, and now you solve for these two equations. Okay, so the solution of this will give us, so I'm not going to solve this. uh, you can treat this as an exercise, and I think all you guys have already solved this part. So, and I think the answer is wrong in this question. For me, the D is coming. C is the answer coming. But in the assignment, I think it is given to be A. So yeah, for me, the C answer is correct. And this is the last question of today's discussion. Uh, if you have anything, you can ask to me. Recording of these today's session will be available on my YouTube channel, which will be Let me show it to you. What is that? So it is called Maths with Prerak. You can go to this channel. You can search it in the YouTube, and you will find this recording of today's session as well. Any questions? Kindly show question 1 to 4. Okay. So question number, yeah. So question number 1 was this, where we need to use the Lagrange multiplier to find out the maximum value of the function given to some constraint. Question number two, question number two, three, four were on the Jacobians. Okay, so first you need to calculate the Jacobian in this question. In the third question, again, this is a question on Jacobian. You need to find out the transformation of the Jacobian. Okay, and the fourth question is also on Jacobian. So you missed three questions, which so three questions were on Jacobians, and the first question was on um, Lagrange multiplier method. So you can see the discussion and the discussion on all these four questions in the recording. Okay, I will upload the recording by tomorrow morning. So yeah, welcome. Thank you for joining, guys. Um, if there is no other questions, we can call it a day. We can stop the meeting and then. Okay, so bye. Let's see you next week.